Hello and welcome to another tutorial video. In this video I will be demonstrating how to construct your own custom model that can then be used by the Tycho software to determine whether or not a candidate detection is that of a real object or a false object. So with that, let's go ahead and get started. Okay, so the first step is to download the Lib Svm file. This is the library for the support vector machine, and then you'll want to extract it. And once you do so, this will be under the Lib Svm 325 directory. The files that you care about are located under the Windows subdirectory. These are the svm predict, scale, and train executables. So once you have identified those files, then you can proceed to the next step. Okay, so at this point what we want to do is generate training data that can then be supplied into the support vector machine, which in turn will generate the model. So what I'm going to do is go to File, Track Analysis, and what I want to do is verify that the current data file is empty. So the data file has a status of empty, which means that there are currently no objects, no examples of true or false objects stored in it, so we are starting from scratch. So if it is not empty, then you will want to click the Start New Data File button. In fact, you can click it either way, and that just ensures that you are starting with a blank, with an empty data file for this exercise. So having done that, what we now want to do is load up a data set, a set of images that we can then use to generate training data. So in this example, I am going to load up the dataset for Tycho User Guide. In fact, this is the DS3 dataset that you can find on the Tycho website. Now, ideally, you would use your own images. In fact, that's kind of the whole purpose of this exercise, is to generate a custom model, a model that is adapted toward your own observing conditions, your own set of image parameters, and so forth. But for this tutorial, I am just going to use the existing data set that is available on the Tycho website. So I'm going to open up these images, and in fact, I've already plate solved them, I've already aligned them. So if you want to take a look here, again, these are already aligned. You can see that from the animation here. So again, you just want to make sure that these are in a state where they can be supplied into the synthetic tracker. So at this point, I am going to start the synthetic tracker, and I am going to use the default parameters. So I use auto threshold, and then I use a default sensitivity of 50%, and I am also going to use a narrow set of limits on the speed and position angle, mainly just to make this fairly quick for this exercise. In your circumstance, you may want to have a wider search, maybe even a blind search on the motion vectors. But again, just to make this fairly quick, I am going to look mostly for main belt asteroids, which will be between 0.3 and 0.8 arcseconds per minute, with 200 to 300 for the position angle. So in this example data set, that yields about 1300 motion vectors. So I'm going to click OK, and we'll go ahead and give it a moment to go through and process those motion vectors. And once it returns, we will have a set of tracks to work with. So here are the return tracks. So you can think of these as candidate objects. So we don't know yet which of these are true, real objects, and which of these are false. So the next step is to determine which of these tracks match up with already known objects. So what you will want to do is make sure that your observatory is set to the same observatory that acquired these images. So in this example, these images were acquired by the Sighting Spring Observatory in Australia, which has the Minor Planet Center code Q62. Now, if you are working with your own images, then you will want to use your own Minor Planet Center code and set your observatory accordingly. Having made sure that the observatory is configured correctly for these images, we can proceed to navigate to File, Load Known Objects from the Track Navigator window. Now this assumes that you have already configured the Known Object module. If you have not already done so, there is an instruction in the user guide on how to do so. So at this point, the tracks have now been matched with the known objects. So again, the purpose behind this exercise is to generate training data. And in order to do that, we need to correctly identify which objects are real and which objects are false. So as a first pass, we have matched these tracks with known objects. Now I will say that depending upon your settings for the match thresholds, which you can find here under Settings, Known Objects, depending upon these tolerances, you may have some tracks that are incorrectly matched with a known object. Now that will not happen very often, but you need to keep it in mind. So for this example, all of these are good matches because the object distance is very small. It's less than 0.2 arc minutes. So here we have 0.043, 0.025, 0.03. These are all very small object distance matches. And so that makes them very good matches. And if you start to see 0.4, 0.5, basically anything 0.4 or higher in the object distance, then that starts to call into question whether or not it is a good match. And that is also another reason why it is very important to make sure that your observatory is configured correctly, that it is set to the same observatory that acquired the images. So again, just keep that in mind, that there may be some tracks incorrectly matched, just depending upon the tolerances and whether or not there are good orbital elements known for that object. So there may be some uncertainty and so forth, where in fact it may in fact be a legitimate match even with a high object distance. So as a secondary pass, we can also make use of the built-in default model of Tycho to compute the confidence score. So again, while that model may not be 100% accurate for your images, and in fact that's the reason why you are pursuing this approach of creating your own custom model, it nevertheless will be in the upper 90s generally speaking, and so it will be a very good starting point. And whenever you combine that confidence score with a match of a known object, then that will help you establish whether or not it is a real object. So in other words, if you have a track with a high confidence and it is matched with a known object, then you can be quite assured that it is likely to be real. And of course, if you are able to visually inspect the track, which you should do anyway, then that will also really establish that it is in fact a real object. Okay, so to make use of the built-in default model of Tycho, we go to Settings, Tracker, and we make certain that it is configured to use the default confidence model and that the sensitivity is set to balanced. So with that, click OK, and then go ahead and run Action Compute Confidence, and then this will evaluate the confidence score of each track. Okay, so at this point we are now ready to go through the list of tracks. So if I click on the first track in the list, this will bring up the image viewer, and if I double click on the track, then it will give an animation. So indeed this appears to be a real object. Now the other thing I could do is go to the track position window and scroll through the list of items here. This is essentially selecting different images and following the object on each image. So again, this appears to be a real object. So at this point what we want to do now is go to the track combine window. And so I have it here. This is the track combine window. Now if you do not see this window, you can go to the navigation panel up here and locate the item labeled track combine. So if you click on this item, then it will highlight this window. If you double click on it, then it will bring this window to the upper left. So Again, this is the track combine window. Now, if you do not see it here in navigation panel, you can try going to the window menu, and it should be located here. So this is track combine, and so here it is. So at this point, because we have established that this is in fact a real object, we can then proceed to classify it as either true normal or true important. The difference between the two is that important will ensure that the object is added to the training data, whereas normal, it might be added to the training data or it might be added to test data. So test data is a set of objects that are then tested on using the model that you created from the training data. So in other words, you generate a model from training data and then you want to test that model on another set of objects. So because this object in particular is what I would consider a normal main belt asteroid, it has very good signal and so forth, I would classify it as true normal. So clicking that button, it is now added to our data file. So if we go to File, Track Analysis, you will see that we now have one object saved in the data file. So it also went ahead and automatically moved us to the next track in the list. So this is track number 2, and as you can see, it has very good signal. It's presented very clearly in the track combine window. So I don't even really have to do the animation to decide that it is in fact a real object. But if I want to, I can go ahead and double click it to bring up the animation. Again, I can scroll through the positions and so forth. So indeed, we have yet another real object. So I will continue to go through these tracks and classify them as true normal. Now here is one that has high confidence, but it is not matched with a known object. So if I want to, I can go ahead and inspect it visually, and indeed it appears to be a real object. And it also has very good signal here in this window. So true normal. Now here again we have another track not matched with a known object, but it has high confidence. So let's take a look. So this one I might want to classify as important because it is a real object and it also has a very low signal to noise ratio. It looks very faint. So this is one that I would be interested in training upon, just to make sure that the classifier is aware that even a faint object like this is in fact a real object. So to do that, I can go to true important. Here again we have another true normal, another true normal. Now here we have one that is medium confidence, and it is not matched with a known object, so we want to visually inspect it. And I am not 100% certain that this is in fact a real object. In fact, if I go through, well, one, I could go ahead and increase the contrast a bit. So it's almost, I would almost say that it is real, but because there are camera artifacts and hot pixels and so forth, I can't really say 100% certain. If I wanted to, again, I could go through the track positions, and it's just too faint to really identify on each of these individual exposures. So the only way would be to look at the substacks. And again, I almost want to say that it is a real object, but if I'm not certain, then I can just click the skip button, which will take me to the next track, or I could just simply click on another track manually. So at this point, we now have, it looks like 15 objects stored. So these are 15 real objects. And the next step then would be to add false objects to the training data. So if we want to do that, what I would recommend is that we run the synthetic tracker again, but this time with speeds and position angles that are not main belt, because You might have a very faint main belt object that it might not have high confidence or even medium confidence, and so if you simply blindly go through here, chances are, especially at the bottom of the list, these are all probably fake objects. So you could probably get away with simply clicking false normal on a lot of these, but just to make certain, I will run the tracker again, but on speeds that are not that of a main belt asteroid. So I might go from 2 to 2.5. As you can see, that has a high number of motion vectors. So we'll just narrow it down a bit. And we'll go from 50 to 150. So this will return, ideally, tracks that are entirely false objects. So with that being the case, then I can go ahead and, yeah, sure, I could go ahead and load up known objects. It won't find any matches in this scenario. And again, after having done that, then I can compute the confidence of each track. So all of these appear to be no confidence. So that being the case, then I can go ahead and declare all of these to be false objects. Now again, I'm just calling these as false normal because they're simply, this is just simply random noise. There's really nothing interesting about them. But I will show another example of noise that you might want to classify as important. Okay, so this is a very good example. What I have done here is I've loaded up another data set, and what you can see is that there are a large number of real objects. And this is because these images were taken with a wide field refractor as a very large field of view, and I imaged the ecliptic, where there are a large number of main belt asteroids. And so what happens here is that with this large field of view, we can very efficiently capture a large number of real asteroids. And so what I can do is go ahead and go through a lot of these and declare these as true normal, and that really speeds up the process. And again, I'm partly just looking at the signal here in this window. This is the presentation of the object. I typically have it at zoom level 4, and you can adjust the brightness as you desire. But anyway, I'm just going to classify these as true normal. And whenever I get to an object that is false, then I'll pay more attention to it. So here are these true normal objects, and it looks like I made a mistake. Yeah, it's going by very quickly. So this one, I probably did not want to declare that as a real object. But let's go ahead and take a look at it. I'm going to double click. So it turns out that this is in fact a real object. However, you'll notice that the reason it had no confidence is because out of the 3 substacks, during 2 of them, the object was in front of a star. And so you really would not want to classify this as a true object because of the high variation between the substacks, which would simply confuse the classifier. So to remove this data point, we can go to File, Track Analysis, and you'll notice that there are 247 objects currently stored, and we want to remove that one object associated with this data point here. So to do that, you can click on the Show Output Directory button, which is essentially a shortcut to local app data for the Tycho program. And if you sort by date modified, then it will hopefully show the most recently modified file up at the top. So conf info raw, this is the data file that we are working on. So if I right click on it and then I choose an editor program to modify it, then I can open it up here for editing, and the second column here, so this is a CSV file essentially. The first column indicates the image, the reference image associated with the data set, and the second column indicates the track number. So this is track number 98. So we want to identify that track number 98. So I simply remove it and click Save. So we have now removed that data point from the training data. So now if you go back to File, Track Analysis, we now have 246 objects stored. So the other thing I wanted to show was what would be an example of a false object that is not just simply random noise, or it might be somewhat random noise, but it's not the kind of noise that we saw earlier. So if we take a look at, well, here's one for example. So in this track combine window, we see this sort of this camera artifact. So if I double click on this track, then you can see again sort of this artifact present in two of the substacks. And so that would be an example of perhaps a false important object. In other words, we want to make sure to reject this kind of object. So I can click on false important to do so. Here's another one, this kind of artifact right here. So it has some sort of signal associated with it, but we don't want that. So again, if we wanted to, I could double click to show the animation. So this is just a false object that it does have some signal, but it's really nothing that matches that of a real object. So I can declare that as false important as well. Here's another one, another camera artifact, so false important. These two right here. Here's another one. So essentially what you are doing is you are training the model to reject these kind of artifacts. So this is a good starting point, and I would say I would be comfortable just to get some idea as to its performance. We have 255 objects stored, and so you know, you might, ideally you would go ahead and train it on more data, and you would include more of those faint objects that are real. So for example, here's another object. This is a real object. It is faint, so I might mark that as true important. But I'm not going to show you a fully comprehensive training set. This is again just an exercise. So at this point, the next step then is to go ahead and construct the model. Now, I would also like to mention that if you have a lot of hot pixels and a lot of these camera artifacts, it's really a better idea to take care of them up front with a good dark frame, for example, rather than rely on a model of this nature to try to eliminate them. And the reason for that is that, again, as you start to get some sort of signal showing through and it starts to resemble potentially a real object, then the performance of the classifier starts to degrade. So if you do have a lot of objects that on the surface they might look real, but in reality it's because they're a hot pixel and they are not actually real, you really should probably, again, try to deal with them up front with a dark frame. And that way you can reduce the amount of overlap between your real and false objects, and you will wind up with a much better performing classifier with that approach. Okay, so at this point we now have a set of training data which we can then use to generate a model. So I am going to navigate to File, Track Analysis, and then what you want to do is click on Generate Confidence Files, and then you want to click on Show Output Directory. So the file that we care about is labeled SVM Data Combined. So right click and choose Copy. And what you want to do is paste that file into the same directory where the support vector machine executables are located. So here I have the path Lib Svm 325 Windows, and it contains these executables: svm predict, scale, and train. So this is the directory where you want to paste that file. So right click and choose Paste. So you have svm data combined.txt in this same directory. So what you want to do is split this file into two. One file will be comprised of training data, and the other will be comprised of test data. So you can go ahead and open up this file, and the items at the top of the list are actually those that are marked as important, whereas beyond that you have all of the other items that are marked as normal. So essentially what it happens is that whenever you mark an item as important, it goes up to the top of the list here, and anything else can then be beyond that point. So what I'm going to do is simply choose some subset of this file here at the bottom will be those objects that I want to be in the test file, and then everything else will be training data. So I've made this selection here, and I'm going to go to Edit, Cut, and then I will save this, and then I will rename it as train.txt. So that is the training data, and then I will create a new text document, test.txt, which will contain those items that I selected previously. And I might want to make sure that I have at least one new line character, so it will end on an empty line. So I click Save. So here again, this is the set of objects that we want to test on, and these are the objects that we want to train on. So I can go ahead and close this window here. And then the next step is to open up a command prompt window. So I'm going to invoke Windows key plus X to bring up this menu here and choose command prompt. And then what I want to do is navigate to this directory. So I will copy it and then navigate to it here. So change directory. And as you can see here, these are the files in that directory. So what I want to do is now train on this file here. So I make use of the SVM train program. And if I do not specify any arguments, then it will tell me the usage of this program. The ones that I care about, number one would be the kernel type. So I want to make this a linear kernel for this example, and I also want to have probability estimates. So these probabilities are used to then compute the confidence score. So SVM train -t0 will give me a linear kernel, -b1 will give me the probability estimates, and then I want to supply the training data file, so train.txt, and then after that I want to go ahead and press enter. And as we see here, it has a wrong input format on what appears to be the last line. So this is because I have an extra new line character, an extra blank line, if you will. So I remove that, click Save, and try it again. So that time it worked, and we now have an output file, train.txt.model. So this is the model that we have finally created. And if we want to perform a sanity check on that model, we can make use of the test data. So go back to the command prompt window, and you will want to run the svm predict program. So if you do not give it any arguments, then it will tell you the usage of the program. So what we want is svm predict, and again we want probability estimates, so -b1, and the test file is test.txt, and the model file is train.txt.model, and we have to supply an output file. And here it says accuracy is 100%, but do not be overly optimistic with that. This is more or less simply a sanity check. So now that we have generated the custom model, we now want to instruct Tycho to make use of it. So navigate to Settings Tracker and make sure to specify Use Custom Confidence Model. And the first step is to specify the path to the svm predict executable. So you can click on Browse, and in this case specify the svm predict file. If you do not see it here, then go ahead and navigate to it in your Explorer window. And then the next step is to specify the path to the what I call the primary model file. So you are permitted to have more than one model. You can have a primary and secondary. So the purpose of the secondary model file, as one example, might be that you might train a separate model on bin 1x1 images versus another model file on bin 2x2 images, if you wanted to do that. Otherwise, you might have it as a good way to compare different model files. Either way, it permits you to have that kind of flexibility, but for this example, I am just going to have one model file. So I'm going to click on Browse, and this is the model that we just created. So that is the path to it. And these default parameters here are usually ideal. The way that the classifier works is that anything with 50% or higher probability is considered to be a likely true object, likely to be a real object. Anything below 50% is likely to be a false object. So 50% and above is therefore medium or high confidence, and below 50% is low or no confidence. So here what we establish is that greater than 90% is therefore high confidence, between 90 and 50 is medium, between 50 and 25 is low, and below that would be no confidence. So you could change these if you want to, but for this example, let us leave them as the default. And with these settings here, you can go ahead and click the OK button. One way to perform an initial evaluation of the custom model is to load up a different data set, ideally one that was not used in training the model. And what I'm going to do is invoke action compute confidence. And what this will do is compute the confidence score of each of these tracks in this new and different data set. And it will again use that custom model to do so. So there are over 2,300 tracks in this list, so it takes a little bit longer than normal. So I'll go ahead and give it a moment to do that. And then here are the results. So just to do a very quick analysis, we can pay attention to these tracks here, the first 26 tracks. So it looks like these first 8 tracks here, these are real objects, and so the good news is that it did assign a high confidence to these tracks. Now track number 9, if I click on that, this is a false object. However, it assigned it a score of medium confidence. So ideally, since it is a false object, it should have assigned it a score of low or none. So this is one that potentially indicates that it needs more training on these kind of camera artifacts. However, it did correctly score these 2 tracks as no confidence, and they are similar in having, again, that sort of artifact. Even though they have high signal, it was able to distinguish that as a false object. Now, if we want to, we can switch back to the default model and see how it compares, again, just on these first 26 tracks. So again, just to reiterate, this is not a very thorough analysis of its performance, but it is a first pass at it. So it just gives you some idea as to whether or not you are on the right track. So we'll go ahead and give this a moment to finish up and see how the default compares. So I scroll back up to the list here at the top. And so again, these first 8 items, these are real objects and same result as high confidence. But track number 9, the default model correctly identified it as no confidence, again, whereas the custom model identified it as medium confidence. So in that particular scenario, the default model is currently performing better, but I have to say, again, I just did a very quick training model or set of training data for that custom model, so it's not really too surprising that it is not yet outperforming the default model. One way to analytically evaluate the performance of a given confidence model is to make use of the track file statistics module. So if you navigate to File, Track Analysis, you will notice that there is a section labeled Track File Statistics, and the way it works is that you specify the path to a given directory, and it will then recursively search that directory and all of its subdirectories for a particular type of track file. The track file in question is labeled track list all. So if you have this particular structure here, this is what you would see as output from the auto run module. So if you do not have these kind of files, then you will need to invoke the auto run module on a given directory of images, and once you do that, then you will have the track list all file. And so you can do this on multiple sets of images, and then that will allow you to evaluate the confidence model on multiple data sets in one pass. Now again, it is important to make sure that your observatory is set to the same observatory that acquired these data sets that you want to evaluate. So in this case, I need to go to Observatory and choose W16 because this is the observatory that acquired the data sets located under this directory. Then the next step is to choose the desired confidence model that you want to evaluate. So I'm going to start off by evaluating the default confidence model, and I'm going to use the balance sensitivity on that model. So I click OK, and then I click the Generate Statistics button. So you'll notice what it is doing now is invoking separate instances of Tycho, loading up that track list all file, and then it also loads the corresponding images associated with that track file, so that it can then proceed to compute the confidence score of each of those tracks. So it's recomputing the confidence using the currently selected confidence model. So this will take a few minutes depending on how many tracks that you have located and stored under that directory. So I'll go ahead and give it a moment to finish. Okay, so it has now completed the evaluation of each of those data sets using the default confidence model. So what I'm going to do now is click on Show Output Directory, and again, this is just a shortcut to the local app data directory for Tycho, and the file that we care about is labeled trackresults.txt. So I'm going to go ahead and rename that because this is actually a CSV file for one, and for another I want to give it a more descriptive name to indicate that this is the default confidence model. So track results default .csv to make it identified as a comma separated value format file. So having done that, I will now open the file, And the first column here is the data set being evaluated, and then the next few columns are associated with indicating the confidence that has been assigned to a true object, and then the last four columns are the confidence associated with a false object. So as one example, if I select all of the cells for the true objects, we have a total of 286 true objects that were detected, and of those 286, there are 278 that were correctly identified as real objects. So we can write this out as 278 divided by 286. So it correctly identified 97.2% of the true objects. Now for the false objects, there is a total of 730 false objects, of which 710 were correctly identified as such. So we can write that out as 710 divided by 730. And here again we have about 97% correctly identified as false. So again, what we're looking for is that if it is a false object, then it should have a confidence of low or none, and ideally it would not have a confidence of high or medium. So we would want these cells to be 0 and these cells to be higher numbers, and then the converse is true with a true object. We want a true object not to have low or none, so we want those to be 0, and we want it to have medium or high, so we want these to be higher numbers. So anyway, this is the performance of the default confidence model across these different data sets. So now what I'm going to do is repeat the same process using the custom confidence model. Okay, so I have repeated that same process, this time using the custom confidence model. So I am going to rename the track result file with an appropriate name. This is custom primary, and again it is a CSV file. So we can go ahead and look at the results. So as before, we still have 286 true objects. That number will not change because we are looking at exactly the same data sets. However, what will change is that we have a different number of true objects correctly identified as such. So here we have 247. So the result there is 247 out of 286. So we now have 86% of the true objects correctly identified as such, whereas before we had 97%. So that is a noticeable reduction. Now for the false objects, again, we still have 730 of those. However, we now have 721 of the false objects are correctly identified as such. So in this case, we now have a slight improvement. We went from 97% to 98.7% correctly identifying the false objects as being false. So these numbers are not terribly surprising because we only trained with, in this example, 250 objects, and most of those were either really bright, really obviously true, and a lot of them were also just really obviously false. So there was not a whole lot of variation. In other words, there were not a lot of examples of here is a true object, but it's really faint, or here is a false object, and it has some pretty decent signal associated with it. So it really does come down to having additional variety, but that's just a matter of giving it more training data. And also just keep in mind, you really want to make sure not to give it an incorrect data point. In other words, if you are not sure if an object is true or if you're not sure that it is false, go ahead and skip it because you do not want to supply incorrect training data. Well, that's it for this video. Thank you for watching, and see you next time.